Hello? All right. May I have your attention, please? Let's get started. Okay. So last time we discovered the need and some tricks for doing Bayesian non-parametrics. Basically, it is about generating a infinite capacity distribution to accommodate potential needs on large data. And the model we talked about is called a Dirichlet process. And it is like this. It is really generating a distribution over the random partition and also make use of that partition to model data. So here is a rough picture. Say you have possible words. A word is basically a partition plus the way it is occupied. Say you have apartheid, and then in each part you can attribute the mass over there with a particular parameterization of a mixture components, and then the real data will be using this particular mixture component to define their own density function. And of course, you can have multiple ways of generating the partition and also to draw the elements inside each of the partition, right? So this is another possible word. And we said how to actually create such a random partition. Well, we take the limit of a Dirichlet distribution, which actually defines a proper conjugate prior over a finite dimensional multinomial distribution. And in this case, we actually have at least the capacity of making this whole thing infinite. Although in a real realization, you only see finite partition because your data is finite. Here we are talking about an abstract kind of extension where if you need more and more partition, this whole process is going to be able to accommodate that. So what is the Dirichlet process? It is about such a partition in which each part is going to actually, the vector of the weights for all the parts is going to take a distribution, defined by this prior, okay? And here you have the scaling parameter alpha and the base measure G null over the sample you actually draw for each of the parts, okay? And this distribution is really handy. For example, it is a conjugate prior in the sense that if you see samples from this distribution, say you actually draw, for example, this pi 1 more time, then your posterior distribution of the Dirichlet process, is going to be this dimension at 1 to represent to reflect the additional mass, right? And then we talked about a number of metaphors to describe and even to help with the inference of this process. And here is a metaphor called the stick breaking process. Hopefully you still remember. So basically the whole random distribution is characterized by two things. One is a random partition of the probabilistic space, and then to draw samples for each of the parts to occupy its centroid. And in this case, we divide them into two processes. One is this stick breaking process. You're going to use a beta random variable to be the pivot to break the stick of unit, starting from the unit length and then down to the remaining part. So you keep doing that. And for each of the stick that you broke from this original stick, you are going to draw a sample, from say this Gaussian distribution or some other base measure. Then you have this match, this atom and also the weight of the atom. Okay, this is to basically avoid a scenario where you draw an atom, but it has a zero probability mass if you treat the whole thing as a continuous distribution. In here, we are defining a distribution in the continuous space, but with discrete samples. Therefore, each atom has a non-zero mass. Okay, and so here these two processes can go in parallel. You can draw the pi's okay, which is the fraction or the weight, the mass of each atom, and the atom from the base measure separately. And then whenever there is this matching between the two processes, you create a dish process. And that defines a pretty handy, a way of writing down the final Dirichlet measure. It is basically defined on this. You can see it's a very obvious form now of a discrete distribution. The mass is only defined on the sample you draw so far. Okay, this is a delta function, which is a 0 for positions other than the argument, and the 1 for the position, overlapping or identical to the atom in here. And then each of these atoms is associated with a weight pi k. Okay, and the whole distribution is defined by a sum of that. Okay, so that's the thick breaking process, and we talked about the virtue of this process being that it inspires you a way to approximate this using the truncation approximation, right? When you chop this stick, smaller and smaller, the remaining mass will be becoming negligible, and then you can just throw them away and work in a finite distribution, okay? And another procedure is known as the Chinese restaurant process. This actually reflects more of a grouping spirit, of data. And also it reflects the fact that the sample from a Dirichlet process is exchangeable, right? So we are talking about how to sit customers in a restaurant with infinite number of tables. And the way they choose the table is proportional to the popularity of each table in the existing samples, right? So in a nutshell, the probability can be defined in here, right? The ith customer comes in, and he look at how the I-1 customer sit in the previous rounds, and then he's going to choose each of the table with the probability proportional to the number of customers already on that table, and then he can start a new table with this residual probability. Okay, and that automatically creates a scheme to group all these different customers. Okay, so this is often used as a mechanism to allow infinite clustering. Okay, and also the way this is grouped is independent of how the customer come in. They can come in any order. Remember, here I didn't even record the name of every customer. They just come in, okay, and they can choose the table. Although in real life, you need to have another thing. Here, we are basically only talking about how to attribute a customer with the table. We are not really talking about how different customers can be different from each other. Here, we only record the fact they are choosing the same table, right? So this is not yet enough to model a distribution of the customer. It's only modeling the distribution of how customers are grouped, but not the customer themselves. Okay, the customer itself could be represented by, for example, xi, and that's a data point whose likelihood is not defined yet. Therefore, we need another layer of mechanism which actually gives you a model known as the Dirichlet process mixture, in which we are going to attribute each of the table with its own parameter, which is actually what we drew before. Okay, for that that atom with a non-zero mass, and then we're going to use this atom to define the centroid of the distribution for the customer or for the data points sitting around this table. Okay, and that basically allows you to now write down the likelihood of the actual data, which is going to be relevant to how customers are sitting around the tables, and also how customers are related to the dishes or the centroid served on each table. Clear about that? So that gives you basically, two different ways of writing down the graphical model for a DP mixture. So here, I have two graphic models representing two different metaphors. One is the CRP, the other is stick breaking. And in here, I make a distinction of the data sample and also the sample coming out of the Dirichlet process itself. Okay, so here, for every data point, it has to have a centroid. And in this particular graphical model, I make explicit that each data point has its own centroid, but different data point can have identical centroid. Okay, therefore, this sample, can be reused by different sample. It's just having a different index, but its value may be the same. So how to ensure that the sample can be reused? Well, we have to define a Dirichlet process prior so that every atom has a non-zero mass, so that the next draw can draw the same atom from the Dirichlet process again. Otherwise, if here I just put a base measure like Gaussian, then every time you draw from a Gaussian, you will get a different atom. Therefore, every data point will have a different centroid. That's going to be useless for clustering purpose, right? And this clustering idea is made more explicit in here, the stick breaking process, where instead of attributing every data point its own centroid, albeit they can be overlapping, here I made explicit that I have a collection of centroids, which by itself can be infinite, but their indexing is different from the data indexing. They are coming from the Dirichlet, coming from a base measure, and they are continuous numbers, and each of them is associated with a weight, which is defined by this pi vector. Okay, and pi vector, remember, it is coming from the stick breaking process, parameterized by a single scaling parameter alpha, using a beta distribution. And then the way you want to group data together is to now introduce, remember we have this trick about introducing auxiliary random variables. Now we use such auxiliary random variable. We introduce this y, which is the indicator of, to which particular centroid this particular data point is associated with. Okay. So this one and this one look different, but they are the same. Here I made explicit that a data point is associated with a particular centroid. Here, I'm basically saying every data point has its own centroid, but the two different points can be having the same centroid. They just have a different way of indexing, but these two are the same. Okay. In here, I can now introduce explicitly, the weight of every centroid to define the probability of this indicator function, okay, being one of the possible tables or one of the possible centroids. So this is the Dirichlet process. Any questions so far and regarding the generative model and the basic statistic manipulations behind that? So it's kind of a cool device which seemingly allow you to generate, having a flexible, device to deal with mixture models because it is infinite. So you don't have to deal with K. Of course, you have other things, which is somewhat reflecting the K-ness, which is this alpha. Remember, alpha is the residual probability of pulling out a new table, okay, if you don't like any of the existing table. And so it still needs to be specified. And the value of the alpha does influence the number of clusters you eventually end up with. But it is a little bit more flexible than set the K to be fixed, say 5 or 6 clusters. Here, there is it is elastic. It is basically giving you the opportunity to allow data to, influence the way number of clusters can be generated. So now we know what is the Dirichlet process. I like to actually maybe give you an example about how this can be used in a real problem, so that you can appreciate its power a little bit more. And in particular, sometimes when a statistical model is presented, it is a little bit hard to specifically conclude its utility, especially in this case, clustering problem. Because we talked very earlier before that clustering is a terrible problem as a platform to compare, power or utility of different models. Because there isn't a ground truth for clustering, right? I give you a cluster of data, and someone say it's 3 class, and someone says it's 4 class, and there's no way to reconcile different opinions. Okay, even if it is your data and you say it's 3 class, I can still disagree and say it's 4 because I just like 4 classes, right? So there isn't a ground truth. I was very lucky enough many years ago to run into a problem which is like clustering problem, but there is ground truth. so that I was able to use that as not only a platform to develop one of the early instance of a Dirichlet process application, but also to hopefully conclude that it is, after all, a useful device. And here is the problem. Okay, so it's a populational genetics problem which actually benefits from good clustering, and then there is a ground truth, if you get the right clustering. Not necessarily the right clustering, but a good clustering. So here is the idea. We're talking about a problem known as the ancestral inference. Again, this is, for those people who are not interested in genetics, it's okay. You can try to appreciate how, an empirical problem can be matched to a pretty fancy statistical model. Remember, this paper was presented in 2004, which was the first year, actually, this whole Dirichlet process was somehow rediscovered by machine learning people, and people are trying to understand what it can do for us. So our goal is to, say, estimate something very interesting, which is called the haplotype in every individual. What is a haplotype? Well, your genetic material comes from your father and your mother. And if I have a microscope to look into your cell, I probably can see what your father's DNA look like and what your mother's DNA look like, right? The truth is that I don't have such a microscope, or it's very expensive to actually get such a microscope to read every chromosome. What I get is basically a mixture of the two things, which is called the genotype. Experimentally, it can be obtained by just take a piece of tissue from you, homogenize it, and sequence it, and then you read is a convolution of these two pieces of information. Okay, so how to deconvolve that? That's actually the question. And this question is interesting because there is ground truth. And your father's DNA is your father's DNA. If I spend money on that, I can actually read it. I just don't want to do it sometime, and by doing but prefer a cheaper process to get this gene, which is a genotype. That's about 1/10 or maybe 1/100th of the cost of haplotyping your DNA. Okay, so now the problem is defined as the follows. I get population data from of genotype from a population, and I want to estimate your haplotype. And this problem, is really benefiting from the following generative model, which says that there are, after all, finite type of haplotypes in the world, at least in every region, because we all derive from some common ancestor, and then your particular haplotype is maybe a noisy version of that common founder. Therefore, if you can attribute every haplotype to their hypothetical founder, you are more likely to pull the statistical power of multiple haplotypes being attributed to the same founder and then get them better estimated. Of course, the true estimation will still take some statistical ingenuity, but that's well defined. And and also this is a constraint inference problem because the two haplotypes to infer, however it is, when they are mathematically put together, they must be consistent with the actual genotype you observed. Okay, so that's the whole problem. Basically, neglect all the genetic background. The take-home message that if you do better clustering here by identifying the centroid, the ancestor, and the association of every haplotype to the ancestor, and then you get a better estimation of the configuration of the haplotype. Okay. And the problem is non-trivial because here the data points to be clustered are not directly observable. They are hidden. What you actually observed is a combination of two such hidden points, okay, existing in the people. Okay, so we were handed this problem by our genetics friends, when I was a grad student. And in fact, there were originally solutions to this already, which is exactly built on a finite mixture model. I'm going to guess, for example, there are, give me 100 people. I guess there are 4 or 5 ancestor, types. And then I'm going to do a clustering of the hidden data and then write the joint likelihood function for the observed genotype. That's what people do. Okay? And now we ask, why 4? Why not 5? Why not 6? Right? So naturally, you can imagine a Dirichlet process to kick in and define maybe, a like this. Let's define a Dirichlet process prior, okay, for the centroid or the ancestor type. And also, you can view this as the mu and this as the sigma in the Gaussian case. Right? One is the mean, one is the variance, which defines the deviation of the real data from the center. Okay, and how many there should be? Well, I put k here, but k here is now a random variable, which follows actually the Dirichlet process. Okay, so that's basically a slightly fancier, generative model with a Dirichlet process prior. Okay, and then how to do inference. Okay, so we talked about one procedures of doing inference under the Dirichlet process already, which is to just cyclically sample every hidden random variables given its Markov blanket. Right, that's the typical GIP sampling procedure. And in this case, you can imagine that I probably need to first make an introduction of some auxiliary random variable to make explicit that a particular genotype or haplotype is associated with one of these founding types, okay, in here represented by a table. And for this, we already know how to describe that using a sampling procedure, right? This is the Chinese restaurant process. We basically, if, for example, if we knew the center and if we knew the haplotype, if we knew them already, we can have no problem attributing each one to a table by running the Chinese restaurant process, right? Rich gets richer. Okay, so now from what I said, do you find something that I just missed? I just actually realized that I wasn't completely rigorous in what I said in terms of how to group a haplotype to a particular center or to a particular ancestor. I said I just follow CRP. Is that enough? Say I have two table, okay, and both tables were actually occupied by 100 people. They're pretty popular. Or maybe there is a table which become more popular. It has 200 people. But if I look at the dish on the table, it looks quite different from my actual genotype, haplotype. What should I do? Should I go with that table or the other table, which may have fewer people, but whose dish is very similar to what I'm actually taking? The second one, right? Okay, so then there is this tension between these two. Should I believe in the CRP or should I believe in the similarity of the data to the center? Well, the truth is that you need to take care of both. Okay, so that actually gives you a sampling procedure which is pretty intuitive. So here I have the generative process from the ancestor pool, which is of infinite size, to the actual data points. And I introduced the C, which is the implicit indicator function. And here, of course, I need to define the generative model, which is art for modelers. For example, here I can have a mutation model. It takes some probability of making this, even they come from the same ancestor, they can be different from the ancestor by a small fraction of probability because the sequence can mutate, right? And I can also have a noisy observation model, which means that if you observe a pair of haplotype already, the real genotype data may still be a little bit inconsistent, meaning that if you have an A here, if you have another A here, you may have a C here, just because the reading wasn't very accurate. But that must happen with a small probability. So all this is to help what? Is to help with how to match a real data to the table in that Chinese restaurant process. I need to define an affinity function of the real data to the centroids. And these are just different mutation model geneticists that would like to have. Of course, if you are a really geneticist, there are deeper meanings to that, which we can maybe discuss in a different class. All this mutation theta and all that tells you the history of the evolution, how long it takes to evolve from here to here, for example, right? And also how bad is your sequencing procedure or microscope. It can be reflected from here. But that's basically outside our story at this point. So we're going to maybe use this stick breaking type of construction analogy to inspire the introduction of this auxiliary random variable. In this case, every data point, in this case the haplotype, is going to be associated with a centroid theta, in this case the ancestral type that you want to actually also estimate. And that gives you now a pretty explicit sampling procedure. So here the hidden variables are what? The hidden variables are basically the C, which is the indicator function between H and A. The H themselves are not observed. the A's are not observed either. Right? The only observed thing are the G's. So it is a pretty challenging sampling question. But now, thanks to all these definition of generative models, we can actually write explicitly the conditional distribution of every random variable given the rest. I'm going to explain in detail one, and then we can pass the others. So here I want to sample C, which is the probability of attributing a haplotype, okay, this one, and given all the rest of the assignments in here, and also the current status of all the ancestors. Okay, basically, I'm in this scenario. I have all these tables already, which are occupied by some haplotype already, and also I have the A here, which is the genotype. It is already known from the previous round. Of course, it is just represented by a sample. Now I have this new guy coming in, and where it should go to. Okay, that's basically the meaning of this C. It is a seed assignment. And as you can see, now the assignment is coming from two pieces, right? One is that Chinese restaurant process, which defines basically the prior distribution of where it should sit. Without seeing that new data points, a priori, I'm going to follow just CRP to give them to the most popular table, okay, with that probability. Of course, other table with smaller probability. So CRP. And then now with the data being observed already, well, where does it observe? It is hidden, right, I said. But this is basically from the previous sample. I'm doing iterative sampling. Therefore, this hidden random variable has a sample instantiation in the previous round. I'm going to make the assignment based on that value. Okay? So now I can now compare this particular haplotype to a potential ancestor it is going to be attributed with. Okay? And I calculate how likely these matches will happen. And therefore, my assignment K is going to be proportional to the product between this piece and that piece. I'm going to test for multiple Ks, from 1 to all the ancestor you currently have. And also, I didn't write one thing, which is that I also have the probability of assigning it to a totally new ancestor, which is this one over the residual weight, alpha, over n plus alpha plus 1. And here, I don't have anything, because there is no existing, there is no existing ancestor for that extra table. What I'm going to do is to define a marginal likelihood of this given only the base measure, okay, which is the prior distribution of A and others. Okay, and I can do this sampling for every incoming H, and remember that the predictive distribution of the Dirichlet process is independent of the ordering of the data. Therefore, whenever I have a new haplotype, I can always treat it as the last haplotype, in my whole collection of all haplotypes. So I basically put the rest of the haplotype as, people who already seated, and then draw that sample, right? And here are equations for other, proposal, right? This is the C. We already see that, and here you can see one is for the existing table, the other is for a new table. And then I can also sample the ancestor. The ancestor, again, is very easy to sample now, because you already have in here, you already have the C, you already have the H, okay? Then it's becoming almost like estimating the sample mean, okay, from the existing Gaussian distribution. This is like the M step in the K-means in the EM algorithm. You just re-estimate the sample mean as the haplotype, as the ancestor type. And the H, well, again, you know the assignment. You also know the ancestor, and then you're going to draw the, use the generative model to say, okay, from this ancestor, I'm going to generate a haplotype like what? Like what I'm going to see to be consistent with the current genotype. Anyway, so these are the list of functions that you will see, in a typical, mixture model problem, and you can get the form, even more explicitly by actually drawing a explicit graphical model for that, okay, and visualize the Markov random field or the Markov blanket of every random variable. So the details are not that interesting, but here is what I want you to appreciate. You run this whole thing, okay, which keep drawing the assignments C, and the ancestor, and the K, the H. And it will, something will happen during that process. At the beginning, you will probably see, because, your estimation of the A's of the dishes on the table are so poor, therefore it may not be very representative of the data. Then what happens is that when the new data come in, it is less likely to, be, sit next to the table. It probably likes to draw a new table because, the dish doesn't look like me, right? And then after you get into enough round of sampling and the table dishes are getting re-estimated on and on from the actual sample sitting around it, just like the EM algorithm, you are going to get more and more sensible estimation of the dishes. Okay, to the point that some of the spurious dishes that you draw in the earlier rounds, just because nothing is good enough, I need to start a new table, now stop being occupied by the customer. Okay, and in those cases, for tables which has 0 customer, there's no need to keep it. You just throw it away, recycle it. Not recycle, just it disappeared, right? So that's basically what you're seeing here. Here, there are many, statistics that I can use to keep trace of the MCMC Markov chain. But here I just document the number of ancestor templates, the number of tables. And you can see it starts from a pretty, a big number, okay, even given a very small sample set, a few hundred samples. And it starts to oscillate, go on, off, having more table, having fewer table. But eventually, after a few thousand samples, they start to stabilize at the number of ancestors that is needed. Well, genetically, you may tell a big story, a funny story. Say, okay, all the humans come from 7 Eves, or in this case maybe 5 from Africa, and so on and so forth. So we are not interested in telling that story, but we at least say this particular number, however the meaning it is to give you now the maximum likelihood estimation of the data. Okay, and again, this is of course not to be equivalent to the ground truth. But remember, in our haplotype problem, we do have the ground truth, okay, for a few benchmark data set. And we can actually compare, the estimated haplotype with the true haplotypes that you acquired at a greater expense. And here is a comparison, right? We have 5 different data sets, and it turns out that in all these data sets, using the EM algorithm, guessing just the number, and guessing multiple times, is not actually getting a very good estimation, but using the Dirichlet process, it gets you a much better estimation. Okay, so at least this graph kind of shows you that, in presence of ground truth, the Dirichlet process is doing something useful, and then there is a reason for us to believe maybe the cluster it is generated is also bearing an interesting meaning at least. Okay, all right. So that's basically a quick review of what is covered in last lecture, the basic Dirichlet process for infinite mixture model, okay, and for clustering. Now let's talk about a few technical extensions for that. So these non-parametric Bayesian models is a pretty big family, and for which the Dirichlet process is just one simplest example. There is another counterpart in the continuous space called Gaussian process, which I used to cover, but I may cover it in the future if we have time. But here, rather than giving you another completely different instance, I like to actually drive this instance deeper to actually see how you make the model richer and also develop some interesting statistic technique. Again, it's hopefully also practical for real applications. So here is the real application. Just continue our problem of haplotype inference, or you can call it population clustering. Okay. So in this case, I have a multi-population problem. And imagine that your data now are collected from Africa, from Europe, from Asia, and from the Oceania, and so forth. And I want you to solve clustering problem for each of the subpopulation. The clustering means that I want to find their ancestor sequence and make a association of the current sequence to their ancestors. So what would you do with that? This is sometimes known as a multi-clustering problem, right? So I think one obvious way is just to pretend that I don't know all this information. After all, they are just human beings. I will just put them all together and then solve one data problem, one classroom problem. Okay, and it is something people do. Okay, and you will see, this rationale may be even less justified in an example I'm going to show later. But anyway, you can do it. But you throw away some information already. This, continental label of population is totally unused. And you may suspect I must have suffered from some loss, okay, by not using this information. The other approach that people would probably try is to maybe solve the 4 clustering problems separately. Okay, I have this data set, I have that data set. Why don't I just do them separately? What's the problem with that? Well, it's certainly legitimate. I'm making use of the partition of the population. But the risk I'm going to experience that you may have this so-called data fragmentation problem. Okay, what does that mean? Well, this is not talking about big data. We're talking about small data. Populational ancestral, populational genetic data can be expensive and sometimes can be legally tricky to obtain. And sometimes you get 30 people from here, 30 from there, and so on. So it is only about 30 people, and you do haplotype inference on 30 people. That's actually a pretty hard problem because you don't have enough representativeness of every haplotype. Every possible haplotype may appear just 2 or 3 times. And we know that in the clustering setting, if we have a small data set, it is very hard to get a stable estimation of the centroids, right? And but on the other hand, if you pull the whole thing together, you have a bigger data, albeit you lose some structure. So there is this tension about solving co-clustering problem completely independently or jointly ignoring the partition. And you have the similar, situation in other clustering problems, say in natural language processing. Say you want to group documents from different journals. Say I have a science journal, I have a PNAS journal, I have a Nature journal, and they are not the same journal, but they roughly have the same kind of guideline in covering topics, right? You have physics, biology, and so on. That's common pretty much to all journals. But maybe some journals have a different bias. Maybe in Nature, you see more biology paper than in science. And in science, you'll see maybe more geology or physics journals. And how to reflect the difference? Well, the obvious way is, of course, to solve 3 separate clustering problems using separate Dirichlet process. But again, you are underusing the data because now your data is just a third of the original. Your estimation of a topic may be less stable, right? And of course, put them together makes the distinction between different journals also lost. So that's basically a problem people actually run into when they do multiple clustering problem. And what is the essence there? Well, I think there is intuitively probably a benefit for solving the clustering problem together. The trick is how to solve them together, or what do we mean by solve them together? I guess here is how I see solving multiple clustering problem together. I have maybe 3 different data epoch, and each of them will have some clusters. And it is likely that maybe each of the data set will have their unique cluster that is only here. But also they may have clusters which are shared across all different places, right? And for those clusters which are shared in different places, they may just use the same centroid. And then their centroid can be estimated more stably because they can use data both from here and from here, right? So now the tricky thing is that how can we build a model, okay, which ensures that I can reuse a centroid used in here, in a different clustering problem. And this is not necessarily trivial because usually, for example, when we define a mu and a sigma as the centroid, these are continuous numbers, okay? And when we just draw a base measure, like a prior distribution of the mu and the sigma we knew that whenever we draw it, we are not going to draw the same thing again next time because it is a continuous distribution, right? Every particular atom has a zero mass, right? And that basically means that the sample, when sampled from a continuous distribution, cannot be reused. Therefore, such a distribution cannot be used as a proper, prior cluster, and they cannot also use for proper prior for a co-clustering problem. What we really want is basically a procedure that allows us to draw the centroids. Here, of course, we also want every cluster in here to be also following a Dirichlet process so that they can be, infinitely many clusters from each point. So suppose I have a DP here, I have a DP here, I have a DP here, and okay, because they are DP, I can at least make sure that the centroid within every cluster can be reused by many different data points, right? But the centroid in this cluster and that cluster, how to make sure they can be reused across different clusters? That's actually the tricky question. Because the centroid location is drawn from a base measure G0, right? And therefore, if I draw a atom from this and use it as the mixture component in here, then the same mixture component cannot be reused in here because they couldn't be redrawn by a second process. Right. So what does that mean? It implies that to define a prior distribution for the centroids or the mixture components of multiple clustering problem, that prior distribution itself need to be also discrete. Okay. Here we are talking about the prior being discrete, but the base measure being continuous. In here, we were talking about the prior distribution needs actually a discrete base measure because that's where you need to draw the mu and the theta from, and the mu and theta need to be reused by different subclustering problems. Okay. So that basically motivates the so-called Dirichlet hierarchical Dirichlet process, where we really want this whole thing, this prior distribution, to be following such a discrete distribution over different atoms. And here is a graphical illustration. Now my G naught, which is the base measure of the base measure of a Dirichlet process, is going to lead to a second round of a Dirichlet process. And here it means that the sample in this base measure can be actually reused in both this Dirichlet process and this Dirichlet process. Okay. So anybody had any questions so far? Do you see the differences? In the previous case, our G0 is what? Is a continuous Gaussian distribution. Okay. And I'm going to draw it for a single Dirichlet process. Okay. And here I have discrete samples. Okay. Now here I'm going to make this into a discrete distribution itself. And then I can draw from it multiple Dirichlet processes. And these different Dirichlet processes can share atoms because their base measure here is discrete. That's the difference. Okay? And this couldn't happen if I use that as the base measure because the two DP cannot share any atom if their base measure is continuous. Okay? So I said it at least n times already. And let's now look at a metaphor, which is culinary in this case, but hopefully it helps you to get a more kind of intuitive picture of how the generative process can be carried out. So we call this a hierarchical Dirichlet process, but the procedure is now known as not a Chinese restaurant process, but a Chinese restaurant franchise, meaning that you have multiple Chinese restaurants. But these different restaurants are owned by the same founder. Therefore, for whatever reason, they don't want different restaurants to be totally irrelevant. They may want to use the same menu, okay, or not identical menu, but at least the overlapping menus. So here is the whole thing. I'm going to now define a master Dirichlet process on the top, which of course comes from a base measure like this. And that's no problem. They come from a arbitrary continuous base measure. And from there, you can draw the table and also the dishes. Okay? And every dish will be different, okay, in your first round. And now I'm going to use this restaurant as the master template to create children's restaurants. Okay? And in this children's restaurant, I need to make sure that whenever they're going to start a new dish, they're going to look from this master restaurant and see the dish over there and copy a dish to here. Okay? And the second restaurant is going to do the same. So you can imagine sometimes these two restaurants may copy a different dish, but sometimes maybe copy the same dish with some probability. At least there are good probability of reusing the same dish in multiple restaurants rather than having the two restaurants completely different from each other. Okay, and the procedure is, the oracle is pretty funny now. It's going to be a little bit more complicated than the Chinese round process. So this guy comes in, and he is going to do the usual, CRP, process, and sit on a table with the probability proportional to the number of customers already there. Okay. What's interesting is when he decides to sit on a new table. Okay. So he's going to now do the following. He's going to now see, oh, I want to start a new table. Where is the dish? There is no dish over there. And then he's going to now go to he will send basically back to the master restaurant, the template restaurant. And over there, he's going to rerun a Chinese round process. He's in that template restaurant. Again, there are infinite tables and infinite dishes. He's going to now choose to sit on one of these tables based on the number of times the dish on the table has been taken by children restaurants. Okay, and so he will be probably sitting on a popular dish and get this dish reused in a children restaurant. But still, he could have a probability of choosing a new table even in that template restaurant. And in that case, I'm going to go above and draw a totally fresh dish from a base measure and put it there and also copy it to here. But that same dish, the new one, once instantiated, become an occupied dish, and therefore other restaurants can use that as well. Okay, so this is a two-layer hierarchical dish process, and here I made the whole thing pretty explicit. You now see, some complicated counting procedure. One is happening in the lower level, one is happening on the upper level. Okay. All right, and here maybe it's interesting to take a look at the graphical model as a result of the extension I just described. So here it is the baseline DP and the stick breaking process. And what's happening in the hierarchical DP case is now that this guy, which was originally the base measure, which was the prior distribution, okay, of one of the classroom problem, now is the prior distribution of the jth classroom problem. Okay, so I have a j such dish process. And to create the dish process, I need to also set up a scaling parameter and also a base measure. And here I define the base measure itself to be another dish process. Okay, and this upper level dish process is now following yet another scaling parameter and a base measure, which can be arbitrary. So that's the two-level hierarchical DP, which is to make sure that your multiple DPs here can reuse the atoms, okay, from this layer. And the translating to the stick breaking process is actually numerically easy, but generatively a little bit less intuitive, because here the hierarchy is not so obvious. And you still have the centroids in here, but these are the centroids used across different clusters. But you have a trickier way of now building the weights. Okay, this weights is no longer following a one-level stick breaking process. It is going to follow a two-level sticking process. Okay, and that actually changed basically the weight distribution of the same collection of dishes in different restaurants. Okay, the restaurant J will have a particular sticky breaking process. The restaurant J prime will have a different sticky breaking process, just to change the weight. All right, and just to wrap up very quickly, once you do that, there are evidence to show you that you get a better inference accuracy, even still in the same haplotype inference problem for now multi-population haplotype inference. And here I have some figures showing you reduction of the error rate, using HDP versus multiple DPs together and versus a few other benchmark programs. Okay, so this is the hierarchical DP. Any questions so far on HDP? Questions? Yes?
So you're assuming you know the number of populations you're looking at? Like the number of clusters at one level?
Oh, okay, good question. Yes, in this case, I know, because it is totally defined by data. I have multiple data epoch, and I think it is pretty reasonable to assume that I just want to do one cluster problem for per data, right? Okay. Another, actually, this hierarchical Dirichlet process actually was somehow co-invented in the same group, using totally different motivation. So here is one motivation I used, in a population genetic space. EYT actually used another motivation. Again, because we were really sitting next to each other in the same office, it is very hard to deconvolve the idea. Essentially, it is boiling down to the same thing. Here, the idea is based on a topic modeling thing. And again, it's just a little bit less intuitive in the explanation, but it is more useful, more often seen nowadays. For example, now say I want to turn the LDA model that we learned before into an infinite topic model. Okay, and that actually was wanted, at the same time when I want infinite clusters for populational inference, but it was a little bit more tricky to get done. Why? Because when we say infinite clusters, we really mean infinite topics. We really mean that we want the topic to be unbounded, right? There are different number of topics. Then, how the topics are used, in LDA is a little bit different from how topics are, or how cluster central are used in the clustering problem. It is more indirect, because here we are really not grouping the documents across different topics, right? For each document, we need to estimate, different topic breakdown, right, in a topic vector. And again, when we naively define an infinite number of topics, we are going to run into the same problem that on article A, okay, I now have, different topics. Then on article B, how can I ensure that, they are modeled in the same infinite dimensional space of the topics? Okay, the next n topic is the same n topic from the first one, even though this n can be infinitely many, right? So this question actually was quite puzzling. And here is maybe again, I found this graphical model maybe more interesting to, in this case, to inspire the extension to the infinite model, or at least to the hierarchical DP. If you look at the history before, we will see around the year of 2004, there are a number of papers, kind of combining the DP idea with LDA, and Dave Bly himself wrote a few. None of these are quite statistically sound until actually EY came in and make this all straight. I don't think he get this graphic model at that point, but if you look hindsight, this is pretty reasonable. So here is the topic model, right? We know that you have n words per document, and each word is going to have a topic indicator, and then every such document has what? This is the topic vector, the topic fraction, a topic weight vector for that article, right? This is the article J, and then they follow a prior distribution. All right, and they have k topics. And now if you look at the Dirichlet process, okay, and in a sense, it's somehow similar to each other. Here, I'm going to now group words, okay, to different clusters. And each cluster is defined by a word frequency vector of whatever dimension. But now in this case, I group them into infinite dimensional. So can we actually use this to build an infinite topic model? That's the question to ask. It turns out that it is not, because now your pi j is for the jth article. And now if you draw another pi j prime for another article, you are likely to sample a different centroid in here for modeling the words. Right? In fact, there is no chance for you to reuse the topic used for the first article. And that's actually a big problem already discovered in that point. No way to reuse the topics. And therefore, here is the HTP graphic model I drew before. What they did is now to somehow generate a pool of infinite topics, use the upper level Dirichlet process, okay, to make a discrete pool of infinite possible topics. And then I treat every article, J, to be by itself a classroom problem, okay? And every classroom problem for that particular article is going to draw from that infinite discrete pool the set of topics that is useful for it. Now you can see that different documents will have a chance to share topics, okay? Even though the weight they share will be different, but the atom, the centroid of the topic will be the same. Okay. And graphically, it is amounts to now defining this pi to be not following just the Dirichlet process. It is going to following a hierarchical stick-pin process, so that the same atom, okay, same set of infinite atoms, gets different weights over different article, but still on the same set of atoms. Okay. So this is basically the infinite topic model, and it is, in fact, by definition, a hierarchical Dirichlet process as well, okay? And then, of course, there are, algorithms for you to do the right inference. And at the end of the day, of course, you need to justify, the correctness of this. And in this case, in our opinion, the justification can be a little bit weaker because there isn't the right number of topics. Therefore, you cannot really argue this one is giving you a better estimation. But nevertheless, in ALP, people often use perplexity to justify the usefulness of the model, the fitness of the model. And the people thus see that this Dirichlet process gives you a flexible way of exploring the whole range of different number of topics and find a most likely setup for the model complexity. Okay, and that kind of gives you a way to determine what is the right number of topics, at least from the likelihood sense. Okay, so this is the two instances of the hierarchical Dirichlet process. And in terms of sampling procedure, I'm not going to discuss in detail, but from this graphical model, I guess you probably pretty much see the picture, right? You're going to do Gibbs sampling over every hidden random variables. And you may want to introduce auxiliary random variables Z for association to one of these infinite cluster components, right? And then the attribute, the actual probability of the Z over this infinite many choices of topics is determined by what? In the DP case, it is determined by the CRP multiplied by a likelihood of the data underlying the centroid. In this case, you can say that is the likelihood of a word under a particular topic. But in this case, because it is a HDP, you are going to, the prior probability of associating a word to a topic is not going to be just the CRP probability. It is the hierarchical CRP probability, right? Going to the first layer of restaurant, go to the second layer of restaurant, you multiply these two pieces together, you get the overall probability of assigning to a particular topic, okay? All right, so that's pretty much how we now grow one dimension of the Dirichlet process into a hierarchical one. And the next dimension that I think it's interesting to at least appreciate or be aware about is how to now, use the Dirichlet process to model time series data. Okay, time series data has some particular, challenge, because it is a evolving entity. Therefore, your topic models, your clustering problem is changing over time, basically, right? And your association of the data to the cluster centroid can also change over time, okay? And here I have two main ideas that I felt interesting. I'm going to only have time maybe to talk about the first one, the second one, and the first one, which is known as the infinite HMM, is actually just a different twist of the hierarchical dish process I just talked about. And for that, if I have time, I'm going to mention a few words, but otherwise you can go home and read that by yourself. It's a pretty straightforward paper. And this one, of course, is new. Therefore, I'm going to spend some more time discussing that. It is called the dependent dish process, meaning that you are going to create dish processes over time, but not in a totally independent way, so that you can keep track about what is going on. And this problem is sometimes also known as the evolutionary clustering. Okay, evolutionary clustering is a very interesting and challenging problem, but that is very different from static clustering, because now your cluster component, okay, in the clustering problem, forget about its dimensionality. Just even in a fixed dimensional model, it is not a static entity anymore. The cluster centroid can evolve over time to form a trajectory. Maybe at time t, your centroid is in here. Next time it is going here. Next time it is going here. Okay, this is just a one-dimensional position of the centroid. And this is t, and this is the value of maybe the mu. But you can also imagine that maybe my centroid can actually appear anytime during the time process rather than from the initial point. Maybe here, as a result of seeing more sample, I need to create a new centroid. Okay, and it also evolves over time and so on. And also, maybe there are some particular cluster that becomes unpopular after a while, and it failed to get any data points. Therefore, that one should disappear. Maybe a abrupt stop here. The whole thing is gone, right? So this is often known as the birth-death process. The whole process can actually emerge and disappear at any time point. And also now we have the additional challenge of not knowing how many processes there. There may be infinitely many, right? So that's basically what we want to address in the evolution clustering problem. And you can easily imagine such problem being useful for modeling text, the historical textual data, right? Topics can change, topics can emerge and can die, and so on and so forth. So I'm going to show you one of the simplest construction of such a evolving dish process, and was done by a student of mine a couple of years ago. Again, we use this Chinese restaurant metaphor to inspire the process, to make it really, really simple. So here's a story. I have this CRP, and I want to use this to, I want to reuse this over time in a recurrent fashion, so that the next Chinese restaurant I built in the second time point is going to be dependent on the one in the previous time point in some way. Of course, actually that how they dependent should hopefully be well statistically motivated. All right, so here is a proposal. I have this CRP. At time 1, we know how to do that already. I have the customer already grouped, and they boils down to 3 clusters, and also with their cluster centroid, the dishes being sampled. Okay, now the second time point, and okay, so this is the first time point. Now I'm going to come into the next day. I get new articles or new people to sit, and so how should we do? Should we start the whole thing anew, or I'm going to make this two thing dependent? Or at least if I'm really doing data analytic and document modeling, I may want to have some continuation, or at least to show a trend or a pattern of how these dishes can change over time. So here's my proposal. First of all, I'm going to copy all the occupied tables to the next day, because they were used in the previous day, must be popular to some degree. Let me copy all that. And I'm going to also put in a sense, ghosts. Okay, no, this table, of course, is not occupied by any sense yet. It just opened. But I'm going to put the ghost customer there to remember what was the pattern from the previous day. Therefore, there are imaginary counts in here. Okay. Therefore, this new guy, when he comes into this restaurant, it is not going to be starting from the ground zero. Okay. It is going to look at how popular this table was yesterday, and therefore I'm going to choose the table accordingly. So he could go to any of this existing table or start a new table. But look at the counts here. Even though he is the first customer, there's already, 6 people over there, okay, which come from the previous day. Okay. Now, let's see. After a few such steps, maybe the restaurant come to a end of this operation on that day. It needs to close. It will basically do a cleanup. It will examine. Are all these tables actually occupied? These are the tables either newly instantiated or inherited from the previous one, and I need to basically decide whether they should be kept for the next day. So here there are a table which is not occupied in the second day, and they should be taken away. Okay, so that comes to our third day, and again I'm going to now put the same thing, imaginary counts from the previous day, and then run the same thing. Okay, so this is called the recurrent Chinese restaurant process, and you can prove a lot of nice properties in the sense that you can prove marginally each of the Chinese restaurant process, is also each of the dependent CRP is by itself a CRP. Okay, if I marginalize out all the possibilities of the previous days and so on and so forth. And also it gives you a lot of modeling flexibility. For example, here I'm assuming a first order Markovian, meaning that I only remember the table configuration from the immediate previous day, right? And there is nothing stopping me from being higher order Markovian. I can remember basically the table configuration for the W previous days. Okay? And I can basically even give them a discount. Maybe I treated yesterday more substantially than the previous days, and so on and so forth. So there will be a schedule, maybe a decay schedule, for you to reweight the customer from different, different days. And you can have all these other tricks. Maybe, okay, so this is basically allowing you to get the counts from more than one previous day. And actually, there's the other thing I didn't say. The dish in here and here, it doesn't have to be exactly the same, right? You can introduce something called a common filter we learned before, the linear dependent process, the linear Gaussian model, to allow a transformation from the table here to here, as long as they are still recognizable. Okay, so this one is going to be different from the first one. And there is a need for that because the customer you are going to receive at the second day might be different from the previous one. And the same chef who is cooking this one may have some variations in his cooking. Therefore, the second one will be different from the first one. In document modeling, if you view all these guys to be a document, even more so. The topic in the second day, even we'll talk about sports, for example, the sports topic yesterday and the sports topic today can be different if there is a particular game taking place here, right? So with that, we now have the way to, inherit a CRP, from earlier timestamps in multiple different ways with enough flexibility to evolve the counts, to evolve the actual value of the topics, and so on. And at the end of the day, you can use it for modeling. And here is actually some plots just to show you the effects from different choices of these tuning knobs. For example, we said that there is this window about the range of dependencies, right, the order of Markovian dependencies. And here it is as long as the whole thing, meaning that, I'm going to pretty much remember the whole thing. In fact, I'm going to decay nothing. The epsilon basically is a decaying parameter in here. And if it's set to 0, then this whole thing is 1, therefore there is no decay, right? And what does that mean? It means that essentially I'm going to ignore the timestamp. I'm going to pull all data together and run a single dish process. Because all the customer I got from yesterday is treated no differently from the customer I use today. Therefore, they will be all counted. So there are basically, no evolution over time and a single dish process for every topic. The second one is, a finite Markovian window and a finite decay. Therefore, you can see a balance of the memory and also the way the memory should be discounted. And in the third case, I'm going to, set no memory. Okay, and here it doesn't matter because I have no memory for the previous data. And that means for every time point, I'm going to run an independent dish process. Right? So these are the two extreme plus something in the middle. And you can see a number of interesting behavior. Here is, I believe, the lifespan of each centroid. And you can see here the centroid has a lifespan exactly 1 because the next day I'm going to kill it, right? I'm going to reuse, then use some new one. In here, the centroid are typically starting from the very beginning to the end because once they're occupied, they are likely to be more occupied. They are very unlikely to be killed in later. If they're not discounted, then they are very likely to be killed unless they become really, really unpopular and so forth. And then once new data come in, at some point, I can start some new table as well, right? But it is not very ideal to show the birth-death behavior of topics. And this one has this nice balance that at every time point, there are new topics instantiated, and the older topics have different lifespan to capture, the evolving topics. Okay, and this is the evolution of the popularity. Okay, and here is the distribution of the duration of each of the topics. And how they look like on real data. Well, again, this is, I'm not saying this can justify anything, but I hope this can at least showcase some of the utility of such a model, which is actually quite fun to watch. Right? So there's this time series data of abstracts from NIPS, which is a major conference in machine learning. And some people already did the word processing and cleaned up the data for experimental purposes. And most analysis before is about cluster NIPS documents, run a topic model of the whole thing, and see what are the topics at NIPS and so on and so forth. But here is what we did. We ran this recurrent Chinese restaurant process, and now you can see a number of things. First is this evolving topic. The same topic, I believe this one is about what? It's about, I don't know. With all these keywords, I may want to say this is a topic about speech. And this is a topic with the words, top words, like this. I may want to say it is graphical model. And here I have reinforcement learning because you see, what? Policy and channel, again, policy is the keyword I only see in reinforcement learning, right? So topic actually is changing over time, okay, as a result of our modeling. And then the duration of the topic is also having this interesting pattern. Some are really short-lived, some can be very persistent. And also the popularity of a topic, can show you, an interesting pattern. You can see this, neural network to be very popular in the late 80s. It becomes extremely unpopular. Remember this is pre-2000, so you don't see the resurgence of a deep neural network yet, right? So it become really not popular, for very well-known reason. And some topics like this guy, I think reinforcement learning, become popular and less popular and so on. And graphic model seems to be peaking the popularity after the mid-90s. And I wish I can go further to see it's probably picking up more speed. Again, so it kind of tells you that this model is doing something interesting, not totally at random at least. Right? Yes? How it is calculated? Good question. So you have the documents, right? Each document is actually measured by its topic weights, right? And that basically gives you the contribution of that topic, being used by one article. is a fractional contribution. And you can just accumulate them, over all the documents. Yeah. Again, this is a kind of a very handy tool to allow you to visualize the data and to summarize data. And this is just the simplest version. And later on, we have a dynamic hierarchical DP. This is a dynamic DP, but you can have a dynamic hierarchical DP and even fancy layers called the storyline model, where the hierarchy gets 3 layers, because now you have not only topics, you also have storylines. One topic can give rise to multiple different storylines, even though they follow the same topic. That allows you to trace the events at a much finer scale on real data. And these are basically, I believe, what is currently running in Yahoo. I'm not sure whether it is in Google or not, but after the inventor of this whole thing, Amr Ahmed, graduated, he joined Yahoo and built a lot of further development on this. Okay, so the roadmap is like following, right? So you now know the language of graphic model, and we also know a number of devices to grow it in different way. Here, I just want to show you the bigger picture. We started from a mixture model, finite mixture model, could be k-means, could be EM, and then we know actually how to actually go maybe keep it finite dimensional, but make it a time series using a type of HMM or common filter type of design, and therefore you can now have this evolving topic model or evolving cluster model, like what Dave et al. Did in the I think what they have a temporal or dynamic topic model in the literature, right? Which is exactly like this. And then you have this DP, which is to blow up dimensionality k, and by replacing the Dirichlet prior with a Dirichlet process prior, right? And it is natural to now also combine these two things to make it dynamic infinite dimensional, which is already, I think, implemented in the paper. And so here's a quick summary. I have 1 more minute talking about the other option. I could just leave it to you, for your home reading, or I can mention a few words. Which option do you want? Maybe I mention 1 word just to raise your attention to that. This is a rather interesting, actually, design principle. So HMM, we all know that. The key in the HMM is this transition matrix, right? And therefore, by definition, you have k states. This transition matrix has to be k by k dimensional. Right? Now you want to have an infinite HMM. What does that mean? It means that you don't actually know the number of states. And therefore, you have an infinite dimensional matrix. Now, what the heck infinite dimensional matrix is? It's not even representable, right? You have this matrix. Forget about this genetics, but basically it is a matrix like this. It is bottomless here and borderless on the right. Not even producible, right? So the trick is that now forget about this transition matrix, okay? Treat them as a collection of multinomial distributions, because in each row here, it is a multinomial distribution telling you which next state you are going, okay, from the current state. And now, if you don't know how many number of next states you are going, you make them a Dirichlet process. Therefore, each of the row here is actually a Dirichlet process with infinite atoms and with a finite mass on each of the atom, okay? And then for the next row, you also have a DP. For the third row, you also have a DP. Okay, you seem to be okay in dealing with the fact that you have infinite number of states. What's the problem in this design? Well, we don't need sum to 1 because every row is a DP is sum to 1. I don't have to care about a column. Column is basically the outgoing probability to different from different states. They don't have the sum to 1, right? Yeah. Any other question? A very, very subtle one, if you're careful enough. Okay, so when you do the HMM, no matter where you come from in the first kind of in time t, you are going to move into a set of states that is common no matter where I come from, right? If I am in New York City and I'm going to basically, fly to all the other cities in the United States, and if I am in San Francisco, I'm going to fly to all the other cities also in the United States, rather than a set of different cities, right? Or I don't want to see the case that if I'm in San Francisco, I cannot fly back to New York City at all. That's not good. Which means that the target of all this transition probability has to be shared across different rows. And now if I'm building dish processes differently or independently for different rows, there is no guarantee. In fact, there is a guarantee that the states won't be shared at all. And from state 1, you are moving to a set of states which is not to be shared by the target when you are moving out of state 2, which is very weird. It is not even legally defined for such a process. Therefore, you want to have different processes, dish processes for different transition kind of event to be shared. And that's why what we need is a hierarchical dish process. All these different DPs should be drawn from a base measure, which is itself a DP. Okay, so that's it. The infinite HMM is basically a HDP, albeit that it is a HDP now with not finite clusters, but infinite clusters, because you really have an infinite number of states moving out of, from time t. But what is infinite? Well, anything that is realized already in your previous sample. That is how do you make the infinite argument, right? As many as you need, but not symbolically or not physically maintaining an infinite list, right? All right, with that, I think I'm done with all the tricks for dish processes, how to make them hierarchical, how to make them temporal, how to make them temporal and hierarchical, and so on. And next time, I'm going to talk about another restaurant experience happened in India, and we can see what kind of thing we can do with that device.